Okay, so this second video on graphing trig functions, we want to take that parent function that we just looked at in the first video for our 6 functions, and start manipulating the behavior, I guess, like the amplitude, the frequency, or the period, moving things up, down, and left and right. So the first one, we're going to start with practice problem set number 1, and we'll do a couple here, and I might jump around. So kind of we'll look through this. But the first one I think about here for A is -5 cosine of 2x. So I want to think about what does cosine look like, right? So in my head, I'm seeing the cosine function, which is right here, and I have this starts up here at 1 and does this nice little curve. But the fact that I put a 5 there, that's going to stretch that highest and lowest point. So that's going to affect the amplitude. So that 5 in front, right here, this 5, tells me what the amplitude is. Now, amplitude is always positive because it represents a distance that you deviate from the line of equilibrium. Now, the fact that it's a -5, the negative is telling me I'm going to have a reflection. Right, just like we had last semester, if you reflect all of your y values, it's a reflection over the x-axis. So when I think about what's happening, just cosine, and thinking about normally cosine starts here at 1, but because there's an amplitude of 5, it's going to start up here at 5, and it would go down to -5. So normally my cosine wave would look something like this. Right, it starts on the peak, goes down, and then it kind of comes back up. Okay, in this case, it kind of looks like a W. But now that it's negative, reflect that image over the x-axis, right? So instead of starting at 5, it's actually going to start at -5. So when you start graphing some of these functions, like if you wanted to show like the different steps, it's fine, like kind of do them dotted or very light, and then somehow indicate, well, what's your final graph? Like make it a little bit darker, a little bit thicker. So I might go a little bit darker and a thicker pen here. And so, I thought I selected. Yep, I did that. Thought I selected just a bit darker color. There we go. So negative cosine would look something like this. Okay, so it's the complete reflection over the x-axis of normal cosine. Okay, and then we have to divide up into 4, right, into these quadrants. And notice what I'm doing process-wise. I got the image first, and then I'm going to go back and label these intercepts, because the image doesn't change necessarily. It's how you're going to label it. Like, is it going faster? Like, is it more frequent? Is the wavelength changed? And so that 2 that I have, that 2 represents the frequency. Okay, so if I have a 2x, that means I'm getting twice as many waves in the 2 pi period. So if I'm getting twice as many waves in the period of 2 pi, that means each of them are taking up half the distance. And so a lot of times to get the new period, I might even say this little, I don't know if it's really a formula, but I'll say, oh, it's 2 pi over b, where b is your frequency. B is that coefficient right there. So 2 pi over 2 means my new period that I need to get a whole wave is just pi. So this length right here is just pi. And so then I'm still going to take that pi and divide it into fourths, into like the quadrants, so to speak. So if my whole wavelength is pi and I divide that equally into fourths, then this would be 1/4 pi. This would be 2/4 pi, which we think of as pi over 2. And this would be 3/4 pi. It's a 4. There it is. And then same thing over here. That's negative pi over 4, negative pi over 2, negative, right there where it crosses, 3 pi over 4, and then this is negative pi. And so again, thinking about those quadrant values, it gets its name quadrant because it's fourths. It's just now we're dividing our new period by 4. The new period of pi, divide that into fourths, and that's how I'm getting my increment markings. So then that's it. That would be my graph. And again, thinking about what changed, the amplitude, remember it's always positive, so the amplitude is 5. The new period is pi because the frequency was 2, and the negative gives us a reflection. Okay, now let's look at another example, part B. 3 sine of pi over 2x. So again, thinking about position, this first number is our amplitude. So we will be having a max and a min 3 units above the line of equilibrium. And this right here represents our frequency. Now, it might seem strange to have a frequency of pi over 2. And it kind of is hard to conceptualize counting pi over 2. But then think about how that's going to change our wavelength. Because to get the new period, we're going to do 2 pi divided by pi over 2. Remember, this is the original wavelength, or the original period of the sine function. So the original is 2 pi. This is our frequency, or our coefficient of b. And I'm assuming it's called a b because your first coefficient could be in front, and that would be your a. The second coefficient you might encounter would be your b. And then you might get a shift, which would be a c, and another shift in the vertical direction, which would be your d. Regardless, 2 pi, the original wavelength, divided by pi over 2. Well, that pi over 2 sort of flips up as a reciprocal, so it becomes 2 over pi. And what happens nicely is the pi's cancel. So we get a new period, the new period or wavelength to represent the one complete wave is 4. No pi's, not just 4. So that's nice. And when I label this, I'm going to use that'll be my very, very last step, is actually to label it out as a divide out that into fourths. So let's get our XY axes. And remember an amplitude of 3. So I know that it's going to come up to 3 and down to -3. And remember, sine starts at 0. So again, we have this nice go up, come down, and go up. Notice I didn't mark any values out. And that's just my preference. I find I can draw a smoother graph if I don't have to try to aim for something on the x-axis. Then I can go back and divide out what I have. So like this was 1/4 of the mark because it's the highest point. This is half the mark. This is 3/4 of the mark because it's the lowest. And that's the ending. And then again, dividing that out into fourths. All right. So remember, the new period was 4. So that's my label right there. And I'm going to take that new wavelength of 4 and divide that into fourths. So that would be 1, 2, and 3. It's just really nice. Having a frequency of pi over 2 allowed my intercepts to divide out the actual pi in its label. And there it is. Again, amplitude is 3. The new period is 4 because the frequency was pi over 2. Okay, very nice. Okay, so we can look at part C next, sine of 2x plus 1. So notice my amplitude is still going to be 1 because there's nothing in front of sine. It's understood 1. A frequency of 2. So remember, 2 pi over 2, which means my new period will be pi. So this is your new period. And then this plus 1 after the fact, that's a vertical shift. So all your y values will be shifted up 1 unit. So, when you think about what does your sine wave normally look like? Your sine wave normally would have that nice, balanced look starting at 0, 0, and, having a wave above and or a branch above or a curve above and a curve below. So now just kick that up 1 unit. So now I'm going to start here. And so that I almost sometimes what I'll do is I'll draw in a dotted horizontal line, not to show that it's a horizontal asymptote, but instead to show that's my new line of equilibrium, right? So I'm pushing everything up 1 unit. If it was a -2, then I subtract 2 and make that my line of equilibrium. Because once you know what your amplitude is, that's how much you're going to deviate from that line of equilibrium. So my amplitude is 1. I know that this is that got pushed up 1. So again, it's sort of my new x-axis. So what I might do is I might erase my curve because I know what the sine wave looks like. And I'm just going to focus on this dotted line, this y equals 1, because that's going to be my new sort of line of equilibrium. So the sine wave starts at 0, 0, but that got pushed up 1, and then there's going to be a high, and there's going to be an equilibrium, and there's going to be a low that's normally at -1, but now it's at 1, and then there's going to be back to equilibrium. So like one curve, one period, when you've pushed it up one, it's going to look something like that. And of course, I'm thinking, it's so weird, like my head's thinking about like music scales and transposing, like up a step or half a step or something like that because of that line. And it reminds me of a music staff. I don't know why. Sometimes my head kind of gets crazy things. And then here's the other one. And remember, the sine wave is always going to start and end on equilibrium like that. So now the fact the amplitude is 1, I still have an amplitude of 1. So I know I'm deviating 1 above and below that line. So now the highest point is 2 and the lowest point is 0. And in terms of our quadrantal values, notice I didn't label them yet. And I'm going to label them on the new line of symmetry to get those fourths. Remember, because everything, like your wavelength will be divided by 4. So here's your period of pi. So that means each of these is pi over 4 because you've divided into quadrants. So pi over 4, 2 pi over 4, which is pi over 2, 3 pi over 4, and then 4 pi over 4, which is pi. And then the same thing on the side, negative pi over 4, negative pi over 2, negative 3 pi over 4, and then negative pi. So again, gives you a nice picture of that sine wave. Okay, now I want to do one more on this video, and I'm actually going to jump to something in problem set 2. I'm going to look at, let's look at 4 cosecant of 2x. Because again, from that first video, when I'm going to be graphing cosecant, I should still be thinking about sine. So I'm going to draw this as if it were 4 sine of 2x. So if I were to draw this, that means that amplitude of 4 is sitting right there, and then we just had a frequency of 2, so we have another frequency of 2. So both, like all sine, cosine, secant, cosecant, all have 2 pi as their normal period. So 2 pi over 2, which means my new period is pi. So I'm going to pretend that this was a sine wave first. So like a sine wave, if this were sine, we'd go up to 4 for my maximum amplitude and down to -4. And I'm not adding or shifting it up, up, down, left, right. So I would just draw very lightly or do a dotted line of a sine wave. Okay, so there's my sine wave. There's my sine wave. Okay. And thinking about that frequency of 2, meaning my new period is now pi, I'm going to divide that new period of pi once again into fourths. So, on like here would have been pi. Oops, change it to orange. Here would have been pi. So I'm dividing that equally into 4 parts. So that would be pi over 4, 2 pi over 4, which is pi over 2, 3 pi over 4, and then 4 pi over 4, which is pi. And the same thing would happen over here. Okay, now when we graphed the secant, cosecant to get those parent functions, we looked at where does the sine graph cross the x-axis, because then ultimately those become your vertical asymptotes. So that's why I, again, like that even on the transformations, like I still like to do the sine reciprocal function for cosecant, because that helps me find where those vertical asymptotes are. Anytime it crosses the x-axis, that gives me the vertical asymptote. And then ultimately, I need to take the branch and turn it upside down. So I'm bound in between these 2 vertical asymptotes, and I'm bound in between these 2 asymptotes. And since it's already labeled from the sine, I don't have to change any of the labels. There it is, right? The highest point was 4. The lowest point is -4. I probably should go back and label that's negative pi. That's negative 3 pi over 4. negative pi over 2, and negative pi over 4. The actual cosecant graph, remember, is just in green. So that the anti-amplitude, so to speak, the part that I have in here, so that's just your sine wave to help you sort of set that problem up, right? But in here, it really would be empty. So if I were to really look at like graph this on a calculator, like that whole part would be blank. It's just the green branches above and below that yellow branch or the yellow highlighted section. Okay, so again, just kind of a quick summary. When you see cosecant or secant, think about the appropriate reciprocal function, because that's going to help you build that the asymptotes and where your graph will cross the x-axis, or where it won't, because those will be the asymptotes.